welcome to this video about the algebra of polynomial and rational expressions. In this video, we will explore multiplying polynomials, factoring polynomials, dividing polynomials, rational expressions, and operations with rational expressions. Before we get heavily into polynomial algebra, let's recap a few important terms. A polynomial is a mathematical expression of one or more algebraic terms, each of which consists of a constant multiplied by one or more variables raised to a non-negative integral power, such as a plus bx plus cx squared. The key pieces to remember are, number one, polynomials consist of one or more terms, of the general form ax raised to the nth power, that are added or subtracted. The sample in the definition has three terms. Number two, the coefficients of the terms can be any type of number. And number three, the powers of the terms can only be non-negative integers, including 0. Let's look at some quick examples. 2x squared minus 4x plus 5 is a polynomial expression, but 2x raised to the 2.5 power minus 4x plus 5 is not a polynomial expression. Why? Because of the decimal exponent. Remember, the exponents in a polynomial expression have to be integers. 0.4x plus 1 is a polynomial expression, but x raised to the negative third power plus 1 is not because of the negative exponent. Now that we've looked at some polynomial expressions, let's look at the different types. A monomial is a polynomial consisting of one term. For example, x and 2 are monomials. A binomial is a polynomial consisting of two terms. X plus 1 and x cubed plus 4 are both binomials. A trinomial is a polynomial consisting of three terms. 12x raised to the fourth power plus 3x cubed plus 1 is a trinomial. A degree is the highest exponent in a polynomial. 2 is a degree 0 polynomial. X plus 2 is a degree 1 polynomial. And x squared plus 3 is a degree 2 polynomial. Now let's move on to multiplying. One of the traditional methods taught for multiplying polynomials is FOIL. This method highlights the need for organization. Multiplying polynomials is an application of the distributive property. The key idea is that every term of each polynomial needs to be multiplied by every term of every other polynomial. One way to help visualize and organize polynomial multiplication is with an area model, which looks like this. Let's multiply 3x plus 4 by negative 2x minus 5. So 3x times negative 2x gives you negative 6x squared. And then 4 times negative 2x gives you negative 8x. Then here you get 3x times negative 5 equals negative 15x. And then here you have 4 times negative 5, which gives you negative 20. So the product is negative 6x squared minus 8x minus 15x minus 20, which then simplifies to negative 6x squared minus 23x minus 20. The area model demonstrates how to multiply every term of one polynomial by every term of the other, and it is expandable for polynomials of any size. Let's try another example. Our terms on the left are 7b to the fifth and negative 2b squared. And our terms on the top are 2a cubed, negative 4a squared, a, and negative 12. We need to simply multiply all the terms, then add the resulting terms together. None of these terms are like terms, so they can't be combined. So our answer is So this is our final answer. As we'll see throughout this video, working with polynomials is almost identical to working with simple numbers. When we think of factors, for example, we may think of numbers that are multiplied to create another number. For example, 2 and 3 are factors of 6. 20 and 5 are factors of 100. Often, we look for numbers' prime factorization. The prime factorization of 30 is 2 times 3 times 5. Because all the factors are prime numbers. Think of factoring as undoing the area model we just explored. Often, the terms of polynomials have common factors. Consider this polynomial. Each term has a common factor of 5a squared. So this can be rewritten as 5a squared times 4b plus 2a plus 3b cubed plus 1. This is the prime factorization of the polynomial. It cannot be factored any further. Sometimes factoring happens in groups. It appears as if this polynomial cannot be factored. Rearranging to group the a terms and the b terms, we have this. Pulling out the common factors, we have this. Now we can see the common factor of 2x plus 1. So we have this. 2x plus 1 times a plus b squared. We can always check our factoring work by multiplying the factors to be sure we end up with the original polynomial. Polynomial division is closely related to multiplication and factoring. Consider the number 6. Its prime factors are 2 and 3. 2 times 3 equals 6. So 6 divided by 2 is 3, and 6 divided by 3 is 2. This polynomial has prime factors of 3x plus 4 and negative 2x minus 5. Negative 6x squared minus 23x minus 20 divided by 3x plus 4 gives you negative 2x minus 5. And then if you do negative 6x squared minus 23x minus 20 divided by negative 2x minus 5, that gives you 3x plus 4. One polynomial can be divided by another as long as the degree of the dividend is greater than or equal to the degree of the divisor. Here's how it works. First, make sure the exponents of both polynomials are in descending order and put a 0 in for any missing in the sequence. For example, 2x squared plus 1 would be 2x squared plus 0x plus 1. Divide the first terms. Here, the question is, how many times does 3x go into negative 6x squared? Then, we're going to multiply 3x plus 4 by negative 2x. Then, we'll subtract the product. Then, we bring down the next term in the divisor, and we repeat. How many times does 3x go into negative 15x? Multiply, and then subtract. There's a remainder of 0, so negative 2x minus 5 and 3x plus 4 are factors of negative 6x squared minus 23x minus 20, as we already knew. Rational expressions are closely related to rational numbers. The word rational comes from the word ratio. Just as rational numbers are defined as having the form integer over integer, rational expressions are defined by the form polynomial over polynomial. Here are some examples of rational expressions. When common factors occur in the numerator and denominator of a rational function, they can be divided to make 1. This is often taught as canceling out, but it actually stems from the fact that, for example, 2 divided by 2 equals 1. We can remove the common factors from these rational expressions. Rational expressions behave like fractions. To add or subtract them, we need to get a common denominator. For example, since one expression has 3x as a denominator and the other has x squared, a common denominator of 3x times x squared can be created. Remember to multiply each numerator by the same factor so that we are essentially multiplying each expression by 1. Now multiply through and simplify. To multiply them, we multiply straight across. And to divide them, we multiply by the reciprocal. And there you have it. I hope that this video has increased your understanding of polynomial expressions. Thanks for watching and happy studying.